At first, I will give you a short overview about the work, then a few words about the concepts of abstract state machines, and then some words about the first results, and also the next steps in this project, and how these results can be embedded in the open S-BPM project. If someone is interested, I can show you the results afterwards on my laptop, but it's not very exciting because I have no user interface and I can show just output from print statements. Okay, since the S-BPM approach has been developed with a precise semantic concept, its representations, the models, are executable, and these are the existing components from S-BPM in the upper part of this picture. Corresponding formal method, therefore, would enable the validation of any S-BPM model, and the abstract state machine, the ASM, has been developed for such purposes and is used for systems engineering. And based on this ASM method, an abstract interpreter has been introduced in the S-BPM book by Mr. Berger. And using this abstract interpreter, it allows to validate S-BPM models and can say execute it on paper. And the idea is to have a corresponding software interpreter which would allow two things. At the one hand, a concise proof of this concept, and on the other hand, it allows the automated execution of models in terms of a workflow engine. This means this executable interpreter based on this abstract interpreter, and so I can prove the concept, and if the concept works, I'm able to execute the models, and so therefore I have a workflow engine. A brief introduction to abstract state machines. Abstract state machines are developed from Yuri Gurevich, 1985, initially called evolving algebras, and is a universal mathematical framework for semantic modeling of discrete and dynamic systems. And very important is states are structure, and this allows very complex data structure. ASMs are based on mathematical algebras, and relations and sets are supported, and therefore really complex data structures like graphs we need for the S-BPM can be built. An ASM consists basically of a set of states and transition rules, and at a particular time only one state is valid, and starting from a defined initial state, a transition to a subsequent state only occurs under a certain condition. And a condition, or the transition from one state to the next state, is driven by a transition rule, and the basic transition rule is if condition, then update. And condition is a Boolean expression, and updates refers to a set of finite assignments which are performed in parallel in the course of the transition. And there are some enhancements in the last year, and so therefore we have, or there are single multi-agent ASMs are available, and also synchronous and asynchronous ASMs. And these enhancements also includes additional transition rules. For example, the let rule. Let x equals t in R means that the value from t is assigned to x, and t could be a value or a return value from a function, and assign this value to x and then execute R. And the scope of x is in R, and R is another rule. And afterwards we see an example where this let transition rule is used. And the next two rules, transition rules, are very powerful. And first one is for all rule. This means to execute R for all x which satisfying alpha, and execute it in parallel. And for the predicate logic, this is equals to the universal quantifier. And the choose rule is to choose in x satisfying alpha and execute R. This in predicate logic is equals with the existential quantifier, and with this rule you can build distributed systems, or especially non-deterministic systems. Okay, ASM, due to the enhancements in the last year, the ASM has developed to a well-founded systems engineering method and is used in software and hard software systems, and can on the one hand use for analyze and on the other hand for specification. And I mentioned before we have the synchronous, asynchronous ASM, and multi-agent and single-agent ASMs are supported. There are many benefits to use ASMs, and also use ASMs for S-BPM. Just four benefits here. The first is the intelligibility, and with the semantically well-founded form of pseudocode, systems engineers are able to transform descriptions from application domain terms into a precise abstract definition. And so this is important for enhancements of the S-BPM language in future, and as a byproduct, such a pseudocode can use as documentation. But you must be familiar with ASMs and should be familiar with the application domain. It's not so easy to read, but can use this as documentation. What does precision means? Based on the mathematically defined semantics, the result is a precise model. And scalability, mentioned before, we have single and multi-agent ASMs, and with this ASMs, sorry, we can build very complex systems, and this is especially for the open S-BPM project important. Think about distributed processes. And execution, very important point, the possibility to validate and verify systems with ASM specification led to development of ASM languages, and with these languages you can, or we are able to execute such ASM specifications. Okay, some words about abstract interpreter. You know subject behavior diagram, and I mentioned before the behavior diagram can be interpreted as a direct graph. You can see it here. And each node represents a state in terms of ASM. And this graph consists of nodes connected by edges. So we have here node A, B, and A and B are services which are assigned to this node. And the functions send and receive are the activities or the services which can be assigned to a node. And a transition only can occur on the activity assigned to a node, for example A, is completed. And in order to manage alternative transition, each edge uses an exit condition. And the next slide show you a typical ASM. This is a pseudocode. And this ASM, this rule behavior, shows how to process a graph. I mentioned before this could be interpreted as directed graph. And this rule behavior allows us to process such a graph. And this ASM can be read in the following way. Each subject is in a given state, and this state is the SID state. And the transition from the current state to the next state within the subject behavior diagram can only occur if the service or the activity which is assigned to the node, to the actual state, is completed. Therefore, the perform rule will be executed until the predicate complete or completed indicates that the service is completed. And we have the rule behavior, we have rule proceed, we have rule start, and the age to be taken to the successor state is selected by the function select age. So here we have the let rule. This means this function select age select one of the alternative edges, assign it to this variable age, and this age is used in this rule proceed. And in the case completed, a service is completed, we are in this let statement, and the proceed rule is performed and set the new state, the current state of the subject to the next state and starts the assigned service or activity on the next node. This means we are here in this node, the assigned service is A. If A is completed, the select age function select which is the right age to come to the next node, and the start rule starts on the next node the assigned service. Okay, the perform, start, and select age are or remain abstract at this moment, and we are able to read. I hope so. We are able to read this pseudocode abstract state machine. Okay, in order to keep the implementation of the executable interpreter as close as possible to the abstract interpreter from Professor Berger, the corresponding tool needs to follow the mathematical definition of pure ISM as used by Professor Berger. And we use Core ISM. It's an open source tool, and this tool fulfills the needs and is an executable ASM language, allows synchronous and asynchronous ASMs, also as single and multi-agent ASMs, has a very small core, but can be extended by plugins. Also the for, all, and choose transition rules are plugins. And it has a Java interface, and this Java interface allows communication with the environment, but I always say the core ASM behaves like the British Queen. The British Queen talks to me only if she wants, and I cannot talk to her. And so it's a bit difficult to embed it in another framework, for example, for a user interface. Okay, this tool, core ASM, we use to implement the executable interpreter. The subject-oriented approach comes along with 5 symbols, and we have 2 levels, the subject interaction diagram and the behavior diagram. And modeling the behavior of a subject is performed through the behavior diagram. And an example, which is maybe well known, the holiday application process. And this behavior diagram can be transformed or interpreted in a directed graph. And this is the structure, or this is basically the structure which I need to process an S-BPM graph. And the rule behavior, or basically with the rule behavior, we are able to walk through this graph, and the current implementation can walk through this graph. Also, we are able to send and receive when this node, this service C assigned to node S2 is a send activity. We are able to send send messages to other subjects, and we also are able to use the alternative send, which is in the method defined. Okay, this brings me to the next steps. At the current implementation, we are able to exchange messages asynchronous. The next step is to implement synchronous sending and receiving, and a full implementation of the input pool concept. We have already input pool, but not with the full constraints. At the moment, we model with our interface from eCore. We have the present not graphical tool to model, and the next big step is freedom of choice, which is defined in the method. It's also very important to embed the workflow engine into a framework, for example, to have a user interface, and make it accessible by the open S-BPM. Some words about the open S-BPM. This project has been initiated to foster the idea and the concepts of S-BPM on a common theoretical and practical basis. And it aims to establish a research platform for S-BPM developments. And as you see in this picture, this is the platform. Here's the workflow engine. And in this platform, or within this S-BPM project, this workflow can be used as a reference system for further developments of the language and process developments. And the next slide brings me to a mathematical precise end of my presentation.
Thank you very much, Mr. Lerchner, for this very interesting presentation. And are there any questions? Yes, please.
So now we just introduced the abstract state machine, and I just want to make sure whether I got it right. So the finite state machine is a deterministic automat, and the abstract state machine is a non-deterministic automat? Or where's the difference between these two state machines?
You can build up with abstract state machines also deterministic and non-deterministic. One big difference is states are structure. For example, a set is a structure, and you can use, yesterday we had gaming at the evening. You can build with abstract state machines Sudoku solver, and the state is the unsolved set. But it's not this, you can build with ASM deterministic and non-deterministic. That's not a problem. Okay.
The key point is that you really manipulate structures, not only a finite number of states. So the structures is really general structures.
Mm-hmm.
No problem.
Sorry.
And with the supported sets and relations and lists and so on, you can build up very complex data structures.
Are there further questions? And there's one from my side. Yesterday we were talking about embedding the organizational context.
Mm-hmm.
Could you explain briefly how this could be done in your approach?
No.
Then we are finished. Maybe I have an idea.
That's we talked yesterday about. In this architecture, this is the workflow engine, and we have to define interfaces, and these are the user organization context, engine, whatever. And we have to define within this project interfaces how we can communicate.
Okay. But could you go back two slides where we had this one back, where we had these this thing with the interfaces. Yes, when you were talking about the English Queen.
Yeah.
You have to be asked, but you can't ask her by yourself.
Mm-hmm.
This could be a problem because the communication is only on the one side. And from my point of view, this is a major drawback. Is there an idea how to fix this problem? Because when you embed a server for the organizational context, you need a bidirectional communication on this topic. So if you can't implement this, then I think you will get a real problem.
That's right, and I'm thinking about how I can solve this problem. Maybe I use an agent with pulsed environment for new information or something from the environment. Event is to work with an event manager or something else.
So one has to implement something like a workaround about this. Okay.
May I interrupt?
Yes.
So if you implement algorithms which has infinite loops, then you don't also never get an answer. And that's the key problem here. You generate structures, and since there's logic involved, it might be that the processes never end or something. If you avoid this, what you in practice really have to avoid, then you settle the problem in a way.
That's true. Yeah. Okay. Any further questions? No? Then thank you very much again for your time.
Thank you.